Hi everyone. In this video I am going to give you another way to calculate rate, this time using what's called the rate law. Before I describe the rate law, let me review from the previous videos how one could get the rate. In the previous videos we talked about the rate of reaction or the rate expression, and given a chemical formula of the form A plus B goes to C, where the lowercase letters are the coefficients and the uppercase are the chemicals, we could get what's called the rate expression or the rate of reaction via this equation. Rate equals the reactants are going lower with time, so we're going to take the negative. Also, we're going to put the coefficient at the bottom. We're going to divide by the coefficient. The change in the concentration of A over some interval of time. And then we can relate the rate in terms of the concentration of A. But also you could express the rate in terms of the concentration of B. B is also a reactant, so it is getting lower with time. Put the coefficient at the bottom, delta B over delta T. If you don't remember why we put the coefficient at the bottom, or some examples, we did go over that in the previous video, and it does make sense for this number to equal the rate. You have to take a percentage of it. If the coefficient, for instance, is 2, 3, 4, etc. Because if the coefficient was, for instance, 2, the loss of A would be twice as fast as the rate of the reaction. So you have to divide it by 2. How about for the products? This one's a little bit easier to grasp. It's positive because the amount of products is growing with time. And again, you divide by the coefficient. So let's say the coefficient here is 5. For every reaction, you make 5 molecules of C. So the rate of production of C is 5 times faster than the rate of the reaction. So to get those two to equal each other, those two sides, you have to multiply the rate, which is 5 times faster, by 1/5 to get it to equal to the rate of reaction. This idea is called rate of expression, or you are writing the rate expression. And yes, you'll be using this equation if you're given concentration over time. You could figure out the rate over a certain interval of time. What is new? In this video, I'm going to show you another way, and that is via the rate law. So that's another way of what? To calculate the rate. And it gives the same number. It is the same rate. It's just different ways to get to it. Same general equation. And in this case, take a look at this. It will be rate equals some rate constant K. Now this rate is calculated based on the concentrations of the starting material. So the concentration of A times the concentration of B, but also sometimes the rate is very tied to the concentration, and you would have an exponent here. Maybe it's squared, maybe it's cubed, but we'll designate it with M and N. Okay. Now, there are a couple things we need to know about this form. Again, this form is called the rate law. These two rates are the same thing. It's just depending on what data you're given, how to calculate for that number. And in a later video, we're going to set them equal to each other and figure out another way to calculate rate. We'll set these terms equal to each other because they're both equal to the same rate. But anyway, let's focus on this, the one with the rate constant and the exponents. Let me just write here rate constant and the exponents. So m and n, I'll write it here actually. M and n, those are called the order of reaction. Order of reaction with respect to A and B. So order of reaction with respect to reactant. Okay, let me get this cord out of the way. Yikes. Okay. Now, these orders, I'll write it here actually also. These are called orders. Before I get more deep into this M and N business, the rate. You'll recall that that is like a speed, miles per hour, but in this case, molarity usually per second. Now that could change. It could be molarity per minute, but it's some concentration per time. Okay, let's go back to M and N. The second thing I want to say about M and N is that M and N sometimes match the coefficients, but not all the time. Sometimes match the coefficients, but not all the time. We're going to have to figure this out, not from the coefficients, but from data. So we will figure out by data. It's called empirical. We're going to use empirical methods to figure out M and N. Empirical? Oh my goodness, empirical methods. You'll see what I mean in a couple minutes. M and N are typically integers, but not always. M and N are typically 0, 1, or 2, but sometimes decimals like 1.5, 1.25, etc. But normally they're going to be 0, 1, and 2. 0th order, 1st order, 2nd order. Okay. Let me give you a graph, and then we'll take a look at some data and calculate M and N. This is the graph I want to sketch for you. Concentration. This one's on the x-axis. And then rate. And rate, we're going to again say it's molarity per second. We'll start 0, 0 in the corner, and then maybe way up here it's 0.020 molar per second. And the concentration, let's go all the way up to, I don't know, let's go up to 2 molar. So what if your rate starts out here, okay, but it never changes? That means that it is 0th order. I'll write it up here, and I'll write it like 0th order. Oh, in A, right? That's our reactant. Pretend that our equation actually is A goes to C. Forget about B. Let's have only one reactant. And we're trying to figure out the order of that reactant. Now, what if it's first order? Well, it has some relationship to the concentration, and if the concentration of A is 0, okay, the rate is 0. But then as you increase the concentration of A and take these different time points, not time points, but data points, maybe it's a straight line. So what are you doing? You're running the reaction with 0 molarity A, no A. Then you run it at maybe 0.5 molar A, and then maybe at 1 molar A, and maybe at 1.5 molar A, and you're forming this line. Same thing, right? Same thing with the 0th order, but here you have a rate at concentration 0 because it is not dependent. This is what it's saying. It's not dependent on the concentration of A. And I skipped a couple steps. So in purple, this means that the rate equals K A to the 0. That's what I mean by the order. But anything to the 0 is 1, so rate just equals the constant. Has no bearing, has no dependence on the concentration of A. But over here, this is first order. And in green, we're going to say rate equals K to the first. Okay, but normally you don't write 1 when it's an exponent. You just leave it blank. As the concentration increases, the rate increases. That's what this green line is telling me, and that's what this equation is telling me. And why don't we use red? Here it starts out very slow, even as you're increasing A, but then it skyrockets. It shoots up exponentially. This is indicative of second order. What is that? I think you can finish the equation before I do. There. So it's square. So whatever concentration you have here, square it, multiply by K, you get the rate. And when you get up to this point, it starts to shoot up because you're squaring it, right? You're squaring it. And it grows faster and faster as you increase the concentration. Okay. All right. Let us continue talking about this idea of rate. We don't know, right? You can't predict this. You have to get this order, 0, first, or second order, via empirical methods. We need data. Okay. We're going to see data in just a bit, but let me give you a couple more things to remember before we see that data. This idea about 0th, first, and second order. Let's use the very simple equation A goes to C again. And let's focus on what does it really mean to be 0th order in the reactant in A. Alright, so it's this line right there. Well, okay, we have the rate. Where do I want to put this? We have the rate equal to K A to the 0, and again, we have it as K. So there are a couple things. The first thing is that we actually do need to put units to the rate constant, right? Here's the rate constant, and we need units. Well, if the rate is in, we said, molarity over second, and you'll look at the data, and if they time it by second, then put per second. If they time it per minute, put per minute. What does K have to be for it to give the rate the units molarity per second? I think it's pretty obvious. K has to be in molarity per second because rate equals K. What else do we want to know about this? What this means is that the rate is independent of the concentration of A. A could be any concentration. The rate is still going to be the same thing. That's what it means for a reactant to be 0th order. It's kind of rare in this case, But if you had another one, like a plus b, yeah, one of them could be 0th order. One of them could have no effect on the rate. What about first order? I want to use a different color. Let's use green. First order. This one's interesting. It means that, well, first we have to give the rate law. Okay. And don't put a 1 there. It's implied there's a 1 there if you leave it blank. And k in, well, if that is molarity, and I gotta have rate as molarity over second, k has to be 1 over second, or just second to the minus 1. You see how that works? 1 over second times molarity gives me molarity over second, and that's the unit we need for rate. What this means is the rate follows the concentration of A. So, another way you could say that, if you double the concentration of A, the rate doubles. It follows. I know that's not how you spell doubles. And what I mean by double, we're going to run experiments. Experiment 1, 2, 3, 4. The same reaction, but at different concentrations of A. And if you double concentration of A from experiment 1 to experiment 2, you would expect the rate doubles from experiment 1 to experiment 2. That's how you want to think of these things. The last one is second order. Second order in concentration of A. And this one's interesting because the rate is really tied, really sensitive to the concentration of A, because whatever we do to A, we have to square it. Okay. But before we get to those trends, what is K in this case? What are the units? Well, that's molarity squared. That's m squared. But I only need 1 molarity at top, because I need this to be molarity over seconds. So definitely there has to be seconds on the bottom, okay, to get the seconds on the bottom for rate. But I have to cancel out one of the molarities in this A squared. So this is molarity at the bottom, like that. You see how that molarity will cancel out one of the molarities in this squared term, and I'm left with molarity over second. And that's the same as what? M minus 1, S minus 1. Now, what is this? Whatever you do to A, do to the rate after squaring it. That's a horrible way to think of it. Let me give you an example. If you double A, and remember, you got to think of doubling as you're multiplying by 2. So if you double A, what do you do? The rate quadruples. Where did I get that idea? Because it's 2 to the 2 times. Because again, this is second order. You square it. And again, you got to think of, you're running multiple trials. If from trial 1 to trial 2, you double the concentration of A. If it is second order in A, then from trial 1 to trial 2 you doubled. You have to square that factor, and that's how much you increase the rate. You quadruple it. It's 4 times. Okay. Now, we're not going to do an actual problem, but we are going to... Actually, we are going to do a problem. But this is not the main type of problem. The main type of problem you'll do using the rate law, I'll show you in the next video. But let me show you the essential math that you'll need to do. So here is example 1. Example 1 says, what is the order of reaction with respect to A in the equation A to be. Write the rate law including numerical value of k with the proper units. So this is easy because, again, we have multiple trials. So think of it as trials or experiments 1, 2, and 3. And as the concentration changes, you notice that the rate doesn't change. Okay, doesn't change. So initially you would say rate equals k to the a, and we don't know m. But because it doesn't change, we're going to say m equals 0. It's 0th order. It's independent. And really, rate equals k. So what is k? Well, it has to be this. If this is the rate, and rate equals k, you're going to say rate equals 0.015 molarity per second. It became easy because the order was 0. The order was 0. But let me show you the math if the order is not 0. Same question, but now the rate is changing. All right, we have trial 1, trial 2, trial 3. What we want to remember, okay, we'll get to this in just a bit, but let me give you a couple of math points to remember. If you have rate 1 over rate 2, you could set these equal to the same k. It's the same reaction at different concentrations of A. It's still going to be the same k. K will apply to all the trials. So k is a constant. So the math works out like this. The concentration of A in one experiment to the m over the concentration of A in a second experiment to the m. So basically, you're just doing something like that, okay? And we're taking the ratio of the two different experiments. It could be experiment 1 and 2. It could be experiment 2 and 3. I like it so this number, this ratio, is a positive, not a positive, but greater than 1. Now, you know from math that that's the same as, I hope you know it's the same as that to the m, okay? And we are solved for m. I know I'm going through this a little bit fast, but I'll show you with this problem how to do this set of calculations. We're solving for m, because when they say what is the order, we need to solve for the exponent. All right. So let's say, oh shoot, the last thing is we got to remember, how do I solve for m now? M is an exponent. Remember, you take the log. So the log of the rate 1 over rate 2 equals, when you take the log of this, the m goes to the head of the table. Log of concentration of A in the first trial, concentration of A in the second trial. Okay, let's figure out m. Question mark. All right. Now you could pick any two experiments. I guarantee you it's going to work. I like the idea that this is pretty big rate, so I'm going to take experiment 3 over experiment, and it doesn't matter. It could be 2 or 1. It will work out. I'm going to do it over experiment 2. So the log of the, actually, let me do it the way I would do this. Let me do it the way I would do this. Okay, I would use this equation. So the rate is 0.240 divided by 0.060 equals concentrations 0.40 over 0.20 to the m. Okay, so I think some of you realize, oh, this is going to be easy. I don't need to do this log business, but I'll do it with the log business. Because if you'll realize, this is 4 equals, and this is 2 to the m. All of you know that that m has to be squared. Okay, but I want to prove that we could do this mathematically. I'm going to take the log of 4 equals m times the log of 2. And that means that the log of 4 over the log of 2 equals m. Because what happens if I warned you that m could also be not an integer. M could be 1.5 or 1.25. Then it won't be as easy to see m if it's 1.5. Okay, I wouldn't even know what this number would be actually. This some number to the 1.5 equals 4, I don't even know. I would have to do it mathematically. But let me prove to you that we're going to get 2 for m. I hope we get 2 for m. Log of 4, oh no, yeah, let's do it that way. Log of 4 divided by log of 2, thank goodness. Oh, I did that without you seeing it. But there's 2, m is 2. So the rate law so far is rate equals k times the concentration of A to the 2. Now, you could use any experiment to get k. I'll write it here. Use any experiment or trial to get k. So we'll use experiment 1. Alright? You just plug and play. So the rate equals 0.015 equals k times concentration of A is 0.10, and now we had figured out m already, it's squared. K equals, k theoretically should be identical regardless of what trial you use. That's why I said you could use any. Divided by 0.1 squared. Okay, I got k equal to 1.5. And what are the units? Well, it's squared, so we have to get rid of one of the molarities. So this is 1 over m dot s. And then your full rate law, including the k, equals rate equals 1.5, up with the units, a squared. Okay. We will do 2 problems in the next video. Again, we'll go maybe a little bit slower so we understand this. And actually, one of the problems in the next video, m is not 0, 1, or 2. It's a very interesting problem where m is not an integer.